Organic Chemistry Part 3, Functional Groups. This is the last video for organic chemistry. The first thing I'm going to do is review oxidation numbers. Real or imagined charges on molecules, on atoms and molecules, are what oxidation numbers are. And we went through this much earlier in the course. But I think it's good to review it now because many of these functional groups will differ in the oxidation number of the carbon atoms involved. So we're going to be using the fact that the oxidation numbers in a molecule add up to 0, and hydrogen is going to be positive 1, and oxygens will be negative 2. So let's say I want to know what the oxidation number of carbon is in the following compounds. So what I would do is I would look at here first and go, okay, hydrogen is plus 1, and there are 4 of them. So that must be plus 4 for the hydrogens. And therefore, this carbon must be negative 4. So that's its oxidation number. Over here, I have 4 hydrogens again. That's going to be plus 4. And I have oxygen, 1 oxygen, and that's negative 2. Okay, so in order to get 0, I need another negative 2. So that's what this carbon must be. Over here, we're going to continue on. I get 2 hydrogens. That's going to be plus 2. I have the 1 oxygen, that's negative 2. Now that already adds up to 0. That means the oxidation number of carbon here has to be 0. And down here we have 2 hydrogens again, that's going to be plus 2. Now I have 2 oxygens. Each oxygen is minus 2, so that's going to be minus 4. In order to get 0, I need another plus 2. So that's the oxidation number of carbon here. And lastly, we look at CO2. 2 oxygens would be negative 4, and then the carbon must be positive 4. So what we see is that carbon can go from a low of negative 4 to a high of positive 4. And this is the gamut of charges that carbon shows within these compounds. And basically what we wind up doing is oxidizing a carbon atom as we go from one functional group to another. All right, now on to functional groups. So here's a chart that lists the functional groups that I'm going to go over with you today. We've already seen the first functional group, which is really a halogen. And so we have the different halogens located here, and they're putting in an X. Now, we use the letter capital R and R prime to indicate a different alkyl group like methyl, ethyl, propyl, etc. And the prime just means that this alkyl group doesn't have to be the same as this one. They can be different, or they can be the same. So let's take a look first of all at the halohydrocarbons, as we're calling them here. The general formula R-X, where X represents any one of the halogens. And the example is methyl iodide, which is a more common name. You can always name these 2 different ways. We can name it as if the iodide is the parent, and then we're attaching a methyl group to it. We can act as if the methane is the parent and we're attaching an iodine to it. So one of these 2 will be the more common, and in this case it's methyl iodide. Okay, alcohols. Alcohols all have the functional group OH, and we have the general formula I-OH, and the example is methanol. Ethers have an oxygen atom bonded to the 2 carbons within the chain, or a group. So you notice that there's no hydrogens here with the oxygen, just the oxygen is within the chain, and that's dimethyl ether. Aldehydes have the functional group at the end of a chain, where we have, here we have the R, this could be another alkyl group, we have a carbon double bonded to an oxygen, then to a hydrogen. Now it can be hard to recognize an aldehyde if you look at the formula written this way, but this is the way we know that we recognize an aldehyde. And mostly you're going to be asked to recognize compounds as one or the other. Next we have a ketone, and many times aldehydes and ketones are looked at together because they both have a carbon atom double bonded to an oxygen. In this case with the ketone, it's on a carbon that's bonded to 2 other carbon atoms. Remember, for an aldehyde it was on the end of the chain, here it's within the chain. And we can see the general formula, and we have propanone or dimethyl ketone, or acetone. So this one has 3 different names. Now acetone is probably a name that you're familiar with. You probably aren't familiar with these 2. So acetone is really the most common name. Then we go down to carboxylic acids. And this is the acid group. If you look at it and compare it to the aldehyde, it's very similar, except we have two oxygens with the carbon and the hydrogen. So we have the double bonded oxygen. Again, this will be on the end of the chain, and then we have to the OH. Now it says an acid, and this is then the hydrogen that is donated by the acid. And we're really using the Bronsted-Lowry definitions of acids and bases, where an acid is a proton donor and a base is a proton acceptor. And here we can see that we have two names again. Ethanoic acid, as if it came from ethane, or acetic acid, which is the common name. This is based on the Latin word for sour. Now we have esters. Now esters have a functional group that's going to occur within the chain, and an ester is from a combination of two different things that are bonded together. We're going to see that a little bit later coming up. And the last group we'll take a look at is an amine group, and of course everybody's familiar with the word amino acids. So an amine group would be located on the amino acid, and we have NH2 for the amine group. We have our NH2. And here we have aminomethane or methylamine. Now methylamine is the most common name for this. All right, so first we'll take a look at the alcohols. Now the group is called the hydroxyl group. And the OH here is not the same as OH and NaOH. Here, there the OH is an ion, but here it's not. These are, this bond here between the oxygen and the hydrogen is a very polar covalent bond, just like the bond in water. This bond here to the oxygen from the carbon group is a polar bond as well, but not as polar as this bond. And so because of the polarity of that OH group, the hydroxyl group, alcohols are very soluble in water. Now the solubility will start to drop if this alkyl group here becomes too large. Then it starts to become more nonpolar than polar. And here are some alcohols here. Now you can see in red that one OH group. It can be located different places. This one down here is two of them. So the first one, let's just go over the naming. We can name all of these as if they came from an alkane. So for methane, we have methanol. So you recognize the name of an alcohol because it ends with OL. So we have methanol, ethanol. We have 2-propanol. Now 2 refers to the carbon atom that the OH is bonded to. Iso also means the second carbon from the end. And that's the common name that we have for this alcohol. Then we have phenol, which also could be called benzyl alcohol. We have an OH group bonded to one of those carbons. And then we have a glycol, which means you have 2 OH groups. And the more OH groups you have, the more soluble in water it would be, and the harder it would be to separate it. Now, other common names we have: wood alcohol for methanol, or methyl alcohol, grain alcohol or ethyl alcohol, rubbing alcohol, isopropyl alcohol, and then antifreeze. So this is the active ingredient in antifreeze, and it has a very low freezing point and a very high boiling point, and thus it protects the water in your radiator from freezing in the winter and boiling in the summer. Now I'm going to ethers next because ethers are formed by the reaction of 2 alcohols where we split off a water molecule between the 2 of them. That's why it's called the condensation reaction or dehydration synthesis. I think I spelled synthesis wrong here. It should be an N. So you can see we're pulling off an H2O, and here's our H2O here. And then we just kind of slide everything together, and now we have our ether. This one would be called dimethyl ether. And here is the first time anesthetics were used, and everybody is used to hearing about ethers and anesthetics. But if you just read the paragraph down here below, you see that the first anesthetic was used in Mass General. At this time it was just called Massachusetts Hospital. In 1846, its use was perfected by Dr. Thomas Morton, who was a dentist, pioneer in the field of anesthesiology. He administered the anesthetic, which was sulfuric ether. And this is him right here. And he's an interesting fellow to note. He was a dentist that actually worked on himself to try to come up with the amount of ether needed to knock a patient out for a certain amount of time. Prior to this, they would have to tie the patient down, and the patient would be awake. And they would strap him down, and people come down and tie him down. And then they would do the operation, which was mostly cutting things out, or amputations. But the use of anesthetics allowed for really modern medicine to begin. You can see here they're removing a tumor from the neck of the patient, Gilbert Abbott. And you can go to Mass General and see the ether dome, they call it, the room where this actually took place. Now I put this one in because this was a very common type of alcohol and it's used today. In fact, I've had it before myself when I had a colonoscopy. It really came into prominence when people heard about Michael Jackson dying when he was administered too much of this. The story goes, for you that may not be familiar with it, that he was addicted to this propofol and needed it to go to sleep at night, or he believed he did anyway. And he had a doctor on call there who was supposed to be administering it. You know, I had a couple of colonoscopies, and I'll tell you, when you have this stuff, you are knocked right out. You don't remember a thing. And when you wake up, as if you just woke up from a regular night's sleep. You feel fine. There was no hangover, or you don't feel woozy at all. This was great stuff for knocking you out. Now, you don't feel anything, but I can understand how somebody could become dependent on this. You know, psychologically dependent, thinking they needed this to fall asleep. And supposedly this doctor gave him too much and he died. And I know that doctor had been convicted, I think, of negligent homicide. And he might still be in jail now, or he might have gotten out. But anyway, it's something that you should be familiar with. Okay, on to the aldehydes and ketones. Now, aldehydes have that general functional group. It's called the carbonyl group. For the aldehydes, it's at the end of the chain, and for ketones, it's in the middle. And we have some common ones: methanal, ethanal, and propanone. So here's methanal. You notice Al for aldehyde. Methanal, common name formaldehyde. Now this comes from the Latin word for ant, which is forma, because formaldehyde can actually come from what they call formic acid, the acid that's in ants and bees and hornets, just about any insect that stings you. And so, but this is the common name, what people know it as, and this is the proper chemical name. Then we can have ethanal, like as if it was from ethane. That's called acetaldehyde. So if you oxidize an alcohol, you can get an aldehyde. And lastly, we have propanone, which is actually from isopropyl alcohol. If you oxidize that, you oxidize that carbon atom a bit, and you can turn it into propanone, which is also called acetone, which is its common name. And you can see for acetone and acetaldehyde how the beginnings of the names are the same. And this refers back again to formaldehyde. This is from the Latin word for sour, because it comes from, you can actually get it from oxidizing ethyl alcohol, and the alcohol that's in wine. So when wine goes bad, it turns vinegary, and you go to making acetic acid from the ethyl alcohol. Hope that made sense. Okay, next, carboxylic acids. None of the acids are as strong as our normal mineral acids like sulfuric or perchloric or nitric, but they still can be pretty strong. One thing about carboxylic acids is they usually have a very strong odor, and you can recognize the odor of these things. For instance, if I go right away to acetic acid, that's the acid in vinegar. You know, it has a very sour odor to it. Formic acid, I mentioned in the previous slide, is the acid that's in bee stings. You notice that all the acids have this group called the carboxylic acid group. They're calling it carboxyl group. And you see how they write it, COOH, because it's very hard to type out these double bonds. So this is acetic acid, also called ethanoic acid. So you can name all of these compounds as if they were from an alkane. You notice that the name ends in OIC. So methanoic, ethanoic. We could have propanoic. Here we have butanoic. Here is butyric acid, is a common name for it. This is from rancid butter, when butter goes bad. And believe me, it does. It goes from being like white, yellowish to brown. And what an odor you get. Brutal. Then we have benzoic acid. This would also be called phenoic acid. And this is an acid that used to be used at one time to cauterize cuts. But they found it was way too strong to put on the cut. It would burn the skin. And then we have some others down here. We have glycine. You notice this is an 2 at the end of here. That's an amine group. Oxalic acid is probably the strongest of the organic acids because it has these 2 of these groups on it. So both of these can donate a hydrogen ion. Oxalic acid, the acid that's in rhubarb. If you have citric acid, which is the acid that's in citrus fruits, it's not vitamin C now. But notice it has 1, 2, it has 3 hydrogens it can donate. Now you notice this hydrogen here is bonded to that oxygen, and it's different than this because here electrons are being drawn away from the hydrogen so much that that hydrogen can be donated. But over here, even though the electron is being drawn towards the oxygen, it's not drawn strongly enough to have that hydrogen donated. So we have 1, 2, 3. This would be called a tricarboxylic acid. This would be a dicarboxylic acid. And this is a slide showing the same thing, only this time we have the formulas done as condensed formulas. So you can see methanoic or formic acid, bee stings and ants from the Latin word for ant. And we'll see formica from that. Acetum for sour for vinegar. And then we have dairy products, Greek pro first, or pion fat, propionic acid, propanoic acid, again, common name. And I mentioned butyric acid from the word for butter, rancid butter. That stuff is so bad that you can smell it even right through the cap of the bottle, even if the bottle was covered in plastic. I mean, you can just smell it. It smells like somebody got sick. Not so good. Okay, on to esters. Esters have the general formula R-COOR, where R is a hydrogen group or an alkyl group. So here we go here. So how do I make an ester? Esters are the pleasant odors of fruits and flowers. So we like esters. So we have, this is carboxylic acid, see the COOH. This would be acetic acid. And this is ethyl alcohol. Now I just kind of wrote the formula this way so you can see how we can draw off, I don't know, maybe I'm not going to show that. We could draw off the water. So here's the hydrogen from the acid combining with the OH from the alcohol, and we wind up making the ester. So the ester has 2 names, ethyl acetate, and you could actually say it's acting like it's a salt. So we have ethyl acetate, and ethyl acetate is in a lot of different products. You smell that also like a nail polish remover. And the odor of this is completely different from these 2 odors. This is completely different too. So again, esters, the pleasant odor of fruits and flowers. And here's the group right in the middle here. Okay. Yep, there we go. All right, and here are a bunch of different esters that you can check out. And notice for the flavoring. So rum flavor is ethyl methanoate, or called ethyl formate, and that's what it looks like. Now we could make it by taking methyl alcohol and acetic acid would do it. That was ethyl methanoate. And here we have isobutyl methanoate, the flavor of raspberries. Now, many times you could have a lab where you can make some of these things in the lab, and they're not too hard to make. It's just that when you're dealing with these organic compounds, they can be very smelly, and there's always a danger of some of them going on fire. A little danger there. This is what we used to always make in the lab, the odor of bananas. Pentyl acetate or amyl acetate, same thing. And you can see how we have, the chain attached here can become longer, be shorter, give us these different scents. Here's oranges, pineapples, apricots, strawberries. Now for strawberries, we have a sulfur atom in here. Now I want you to know, how do we see that sulfur atom in the name? Thio, down here. Thio always means sulfur. So if you hit thio as part of a word for an organic compound, that always tells you sulfur is involved. All right, so let's see if you can draw the structural. And I said skeletal, leave off the hydrogens. Just try to do it with the carbon atoms in the functional group. So see if you can draw the skeletal structural formulas for the following. So you want to pause the video at this time and then draw them on a piece of paper and then come back and check out the answers. Okay, here they are. Here is N-butanol. Now N means normal, so that means that the OH would be on the end. We could also call that 1-butanol. Propanal. Now, Al tells you it's an aldehyde, so it has to end with CHO, and the C is always double bonded. Now, you could have the double bond up here to the oxygen, or it doesn't matter which way you put it. And the PROP, like from propane, you notice 3 carbons in a row, single bonds. Now we have down here 2-butanone, so ONE means ketone. And the ketone means a double bonded oxygen is to a carbon within the chain, and 2 tells you what number carbon it is. Then we have propanoic acid, so we know what the acid group is going to look like. Again, propane, and here we go, 3 in a row, and you notice that this looks pretty similar to my propanol. All right, so how did you do? Okay, and the last one we're going to look at is an amine group. So amines are organic bases with a general formula R3N. So let's take a look at methylamine and ethylamine. So here we have, and the reason they have R3, I'm sorry, on this, I should mention that, really 2 of these are hydrogens, if you notice. It's going to be NH2, and then the CH3 is together. So I might argue about that general formula, but that's what they had here. This is from the slides from the text. So this is methylamine, and this is ethylamine. And you can see now they're reacting here with water, and these are our products. Now remember we said it's a base, and here a base would be a proton acceptor. So this is the base, and then water is the acid. And so water is donated an H positive to that, and here's our product. Now, we could have just, I don't know why, this is again from the textbook slides, but the CH3 is really the R right here. And then we have ethylamine, and again, now it's reacting with hydrochloric acid, so it's going to accept the hydrogen from the HCl. Okay, and that is the end of the video for part 3.